Okay, so welcome back to another video. So here today we're given a proof that we want to verify for each of the three statements. So if we're given that capital F of x equal to the definite integral from 1 to x of 1 over t dt, if it's defined for x strictly greater than 0, we want to show that part A that f of xy is equal to f of x plus x, f of y, f of x over y is equal to f of x minus f of y, and then f of x to the power z is equal to z times f of x. So if you notice with this definite integral, if you were to explicitly, evaluate this, you will notice that capital F of x is exactly the natural log of x. And by using that, by using your logarithmic properties to validate this, which yes, it does work for all three of the statements. So that would be too easy of a video to, film. So instead, in this situation, we're actually not going to use any logarithmic properties, any of that stuff at all, and just use what we're given. So with this definite integral, and use that integral to help achieve each of the following, statements that we want to prove. But that's actually not as bad as you think, because with definite integrals, if you know in calculus that if you actually use the properties of symmetry of the intervals, then we can actually use that to our adjustment to define these integrals that were given, plug those back in, use that symmetry property, and then just work our way from there to actually show the left hand side is equal to the right hand side for each of the three. So for each of the proofs that I'm going to do for A, B, and C, I'm going to actually do this in each color at a time. So one color for part A, another color for part B, and then another color for part C, just so the flow of the distinction actually works together. So at least it's easier to read from each. So let's actually just jump right in. Okay, so now for part A, so capital F of xy is equal to f of x plus f of y. So for A, so we need to figure out something about y. So if we're given that x is greater than 0, that's actually fine. So, with this integral, of course, that's we're given. But, we have no restrictions for y, but we want to be careful on our choices for y that we choose. So in this situation, we would actually like to choose, separate this into two different cases. To make this a little better, how about we put this as, we'll do one case for y is strictly greater than or equal to, y is greater than or equal to 1, and then another case for when y is strictly less than 1. For the case that, put it like this, so yeah, for, lowercase numeral for 1 is for y greater than or equal to 0. Then we can separate the regions as for our interval as 1 is less than or equal to t, which is less than or equal to x. And then another one for x is less than equal to t, less than or equal to x times y. So with this, we can actually use the idea with symmetries of integrals to actually write ourselves, a new integral, the sums of integrals, and then eventually we can work our way to achieving the right-hand side. With this, let's see, so we have capital F of x times y. So obviously, if we just plug this back in, so we have 1 and then all the way up to xy as the upper bound of, I'm going to put this as dt over t, okay? Then we can, of course, use the properties of symmetry, so we can separate this from 1 to x of dt over t. And then we add this from going from our interval from x to xy of dt over t. We know that specifically this is just f of x, capital F of x over here, so that's fine. So now we just have to figure out how to calculate our bounds from x to xy. So now let's actually calculate this. So let's see, we have f of, the integral from x to xy dt over t. Suppose that we actually can do a substitution. So let t equals x times u. And so if we differentiate both sides, we have dt is equal to, So it's u dx. Excuse me, I got that backwards. It's supposed to be x times du, because we're differentiating in respect to u, because x in this case is a constant. or rather a number greater than 0. Now with this, let's actually put the substitution back. So we have, now we calculate our new bounds. Of course, we plug x, put that for t, then over here, this is going to be u is 1. Then the upper bound xy, so that means u would be, so the upper bound was that u would now become, xy would now become just y. Then x du, we just put back the substitution, then put t, so x times u. And so those cancels out, so we have, what's it, so y, 1, then this is just du over u. Then it's just equal to, now this is just f of y, since that's just a dummy variable. And then we can actually put this back into our substitution over here. Now we put that substitution back over here, and we can actually see that indeed we have that, we just validate that now f of x, y is equal to f of x plus f of y. So that's actually this first case for part A. So now we have to focus on the negative. So, well, not really negative, it's actually supposed to be strictly less than 1, so don't forget there's also 0 included. So now let's move on to that second case. So now 2 over here is, now we have to focus on the negative, or I keep saying negative, it's supposed to be strictly less than 1. But it actually follows similarly that if you do the same thing, because it generally is exactly the same thing. So now if we separate this out, so I can write this new bound f of x. So I'm gonna write this a little bit differently. So we have, because that's strictly it's less than 1, that means for whatever you just plug in, so that means it has to be, no doubt, xy in this situation has to be less than x. So now in this case, I'll write this as f of x, but we'll separate this, with the symmetry of, integrals, of course. So we have 1x dt over t, that's just equal to 1 xy dt t, add this with the integral from xy to x of dt over t. Then if you actually just see that, okay, so this is just f of xy, so I'm gonna put that, I'm actually gonna put that down as that, fxy. All we have to do is just calculate this integral, so that, which of course, in reality, that's actually very easy because again, we're actually doing this very similar method just like this. We call substitution, dt t, then what is it? We're gonna let t equals x times u, then do the differentiation, so dt is equal to x times du. Then over here, we're gonna now put back the substitution, so now we have, this is gonna be from y to 1 of, this is actually supposed to be x times du, and then divided by x times u. So, and don't forget that we have to flip the bounds, so I can put this as negative and then y1, so we have du over u, and so that's just equal to, in this case, negative f of y. And so now we just showed that f of x is equal to f of x times y minus f of y, but you can just put that further and say that f of xy is equal to f of x, and then add this with f of y. So in both cases, this works. So we have just shown that for both cases, y less than 1 and y greater than or equal to 1, that we actually get the same results, just like that. So part A is now complete, so now we move on to part B. So I'm gonna actually move part B, write part B in black. And it's actually, part B is just the similar method, just like part A. And you're gonna see, and basically because we do this use substitution, you're gonna see that a lot, just, saying. B is, we're of course going to do the same method. So now suppose that in this situation we have y is greater than 1. Now the way we split this integral, that means we have y is less than t, which is less than or equal to x over y. Then that would also have to mean that, x over y is less than or equal to t, which is less than or equal to x. Simply because with our choice of y, we have this is considered, like rationals. So now if we start off with f of x, okay, f of x is equal to x1 dt over t. And so we just let this equal to now f of, or hold on, we're not writing in terms of function, we're still writing this in integrals first. So our bounds would be from from 1 to x over y dt over t. Add this with lower bound is x over y, then that's 1, or actually, excuse me, that's supposed to be x. I don't know what I'm saying. X, then dt over t, right? Okay, and now we just know that this is actually just f of x over y. So let me actually distinguish that and say this is that. So now we just have to evaluate, figure out how to put in the right integral over here. So now we just do a substitution, let t equals, now we're gonna let x over y times u, then dt is equal to, so if we differentiate in terms of u, so this is just x over y du, do the substitution. So now we have a new bounds, of course. So the new bounds being that this is gonna be, the lower bound is x, or rather, that was the original, so we have the new integral, so, okay, so new bounds, x over y equals t, so u would be 1, and then x, that would be, the upper bound would be y, and then this will be x over y du, and then divided by x over y, and then let's just cancel each, actually this will just be times u over here, and then they'll cancel out. Then we have, this is just y1, then cancel, so du over u, which indeed this is just equal to f of y. So we just established over here, so now f of x is equal to, what is it, f of x over y, which is now add this with f of y, then we can see that indeed f of x over y is equal to f of x minus f of y. So that's done. So now let's actually do the second case, which is just dealing with y is less than, y is less than 1. So that would mean that this is going to be the opposite. So now what will change is that we have 1 is less than equal to t, less than equal to x, and then the second with the symmetry is x is less than equal to t, less than equal to x over y. Okay, so now in this case we'll start off with the function f of x over y, which is then equal to the integral. So let's see, this is 1, and then x divided by y dt over t. Then we'll split this as 1 to x dt over t. Add this with the integral from x over y, and then x over here dt over t. Okay, then we know that this piece here, that's actually just f of x, capital F of x. Now we just continue further, then we just have to evaluate this integral over here, but again, we just have to do the substitution. So we let t equals x over y u, then dt is equal to just x over y du. Then over here we have our new bounds that this is going to be from, so the lower bound would be y, and then now the upper bound would be 1. So then we put this back as x divided by y du divided by x over y, then times u. This cancels out, so we have that, and we also have to flip, the bounds too, so that would be negative y1, then this will be du over u, which is equal to negative f of y. And so with this clarification we see over here, we see that f of x over y is indeed just equal to f of x, then add with the negative, so subtract f of y. And so we just, proved the second case. So we're done with both of the cases, just like that. And so there's one more to go, and we want to show that f of x to the power z is equal to z times f of x. But actually, this is actually the much easier part. Z can actually be any real number, and it'll still be okay since that's the exponent. And if we, like I said earlier about the integral, that evaluation is the natural log of x, and we just look at that way. I know we said we're not supposed to use logarithm properties, but I'm just gonna, establish that just to reiterate and say that this is okay. Throughout careful inspection, because what we want to do is actually essentially just do another substitution. We don't have to do any of these cases in this method of, with cases and then more substitutions, but but this substitution is going to be a little different, of course. But if you choose your substitution carefully, if we let u equals t, then to the power 1 divided by z, or in other words, if you can write this as t is equal to u to the power z, then we just actually differentiate both sides. So then dt is equal to, so just use the power rule, z times u to the power z subtract 1 du, right? Now we see that f of x to the power z, so that would have to mean that we write this integral, just plug that back, so it's 1 x to the power z dt over t is equal to, so we just plug in our new bounds, x to the power z is right here. That means u would be x, and then over here, so for 1 is equal to t, so yeah, that would have to mean that this is just 1 over here. Then we just plug in the substitution, so zu to the power z subtract 1 du, divided by, with the substitution u z, okay. In this case, z is just a constant, z is a number, so I'll just factor that outside. It's not dependent for our integral. So this is 1 x, then u to the z minus 1 divided by u to the z dz. In other words, this is just x1, what was it? So that cancels, so we're just left with du here. So -1, so that'll move on the bottom. So du divided by u, which dummy variable, does not matter how you choose it. So in other words, we have shown that this is just z times f of x. And so there we have it. We actually just finished the third statement of the proof, and that's just like that, we're done. So yeah, this is actually a very interesting proof. I know I kind of rambled on a bit, or kind of did a little bit of some messing up, but sometimes I like to double check and make sure what I wrote is actually correct before I actually want to move on to the next step, and so on and so forth. But yeah, I like this proof. Without having to use logarithms and validating these statements, this is actually a really neat exercise if there's any out there, like very similar to this fashion. So yeah, that's pretty cool if you ask me.